In this video, we're going to take a look at differentiability. Now, by definition, a function is differentiable at a value a if f prime of a exists. So that means that we can find the derivative at that value a. It is differentiable on an open interval from a to b if it is differentiable at every number in that interval. Now, what does this mean? So finding f prime of a means finding the limit or finding the derivative at that value a. So therefore, a function is differentiable at those points where the limit exists, meaning where it is defined. So let's take a look at an example, because often most or all polynomials are differentiable. So we want to take a look at points where it isn't. So this often happens with piecewise functions. So let's take a look at this one here. Suppose we have f of x is equal to these two pieces. Now if I graph them, let's take a look at this over here. So we have 2 minus x, so we have a y-intercept of 2 and a slope of -1. So we have this line right here. And it includes the value of 1. So we're going to put a solid point there. And then we have the second piece, which is 1 over x. And we know that's a curve that goes down like this through 1. So we can see that it is connected. So it looks like that it would be differentiable everywhere on this line and on the curve. But what about right at that point when x equals 1? So what we're going to do is we're going to find the limit at that value. As h approaches 0, so we're going to actually find the derivative of f of 1 plus h minus f of 1 divided by h. So we're using the definition of the derivative. So we have to do both sides of this piece. So we have the right-hand derivative, and we're going to use 1 over x as our function. So we have the limit as h approaches 0. And using this limit here, we're going to put in 1 divided by 1 plus h, and then minus 1, or f of 1, so it'll be 1 over 1, which is 1, all divided by h. We're going to do some simplifying by joining our fraction in the numerator. So our common denominator is 1 plus h, so we have 1 minus 1 plus h, all divided by 1 plus h. Now instead of writing this big long line and then dividing by h, I'm actually going to write it beside it and put divided by h like this. So we now have limit as h approaches 0. Simplifying our numerator, we have 1 minus 1, which is 0. So we have negative h divided by 1 plus h. And then divided by h means we're actually multiplying by 1 over h, changing it to a fraction. Okay, simplifying some more because we can see that our h's cancel off. So we have negative 1 divided by 1 plus h. So plugging 0 in for h, we get negative 1. All right, so now let's compare that to our left-hand derivative. Left-hand means that we're going to use the function 2 minus x. So we have the limit as h approaches 0 of 2 minus, and then we have 1 plus h, and then minus f of 1, which means that we have 2 minus 1, all divided by h. So this gives us 2 minus 1, 1 minus h in the first bracket, and then in the second bracket, we have minus 1, all divided by h, as h approaches 0. Remember to keep bringing the limit down because we only can remove it once we plug h is 0 into the function here. So keep on simplifying, we get negative h divided by h, and this simplifies to negative 1. So the limit is negative 1. So since the left-hand derivative and the right-hand derivative are the same, then therefore the limit exists. So let's write that down. Since the right-hand derivative equals the left-hand derivative, the two-sided limit exists Okay, so because it exists, then therefore f prime of 1 is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1, all divided by h, and this equals negative 1. So since the limit or the derivative exists at the x value of 1, then we can see, or we know, that this function is differentiable at x equals 1. So this shows that f is differentiable at x equals to 1. So if we look at the graph above here, we can see that the function has a tangent line at every point, meaning that all of the curves, no matter where I draw a tangent line, there's going to be a tangent because all of this curve is going to be smooth. Okay, so this leads us to a theorem that says that if f is differentiable at a, then f is continuous. So if you can find the derivative at a point a, then we also know that that function is also continuous at that point a. Now note, however, that the converse of this theorem is false. So the converse is that there are functions that are continuous, but actually they're not differentiable. So however, we can get that if f is not continuous at a, then f is not differentiable at a. So let's take a look at two examples where a function is not differentiable. Now, if you take a look at this one here, it looks very similar to the one that we just did. We can see that there's a line here, and then it looks like we have a parabola. So all we need to really check is what is happening when they join together. And that happens looking at this piecewise function that occurs when x equals 0. Now, it looks like that might be a corner, which I'll talk about in a little bit, but it's hard to tell. So we actually need to do some left-hand and right-hand derivatives to check to see if they are the same. All right, so left-hand derivative. We'll start with the left one this time. So we're going to find the limit as h approaches 0. So this is going to be our left piece, which is 2x. So we'll go 2 times 0 plus h minus 2 times 0. We're using 0 because we're checking at the x value of 0. All divided by h. So simplifying our numerator, we get 2h divided by h, which reduces to 2. So our left-hand derivative is 2, which actually means that the slope is 2 at the value when x equals 0. Okay, let's check the right-hand derivative. So we have the limit as h approaches 0, and we have 0 plus h minus 0 plus h all squared. So that's our first part, minus 0 minus 0 squared, which you don't have to write, but I'm writing it down so that you can see the definition of the derivative being used here, all divided by h. So this simplifies very nicely, and we get h minus h squared in the numerator divided by h, and we can reduce everything by h. So h divided by h is 1, h squared divided by h is h, and plugging in 0 we get 1. So the right-hand derivative shows that the slope when x equals 0 actually has a slope of 1, whereas the left-hand derivative shows it has 2. So therefore, the left-hand derivative does not equal the right-hand derivative, even though f of x is continuous. So we can see that it's continuous. We can show that it's continuous by plugging in 0. When we plug in 0, we get 0 for the left piece, and we get 0 for the right piece. However, the left hand and the right hand derivative are not equal, so therefore, the two-sided limit f prime of 0 does not exist. So f of x is not differentiable at x equals 0. Okay. Now remember, in order for it to be differentiable, the left-hand derivative and the right-hand derivative have to be the same. I'm going to show you a second possibility where a function is not differentiable, and this occurs when the curve has a vertical tangent line when x equals a. So this means that the tangent line becomes steeper and steeper as x approaches a. Now f is continuous at a, and the limit of the absolute value of f prime of x is actually equal to infinity. And since infinity is not a number, the derivative does not exist. Let's take a look at this example. Now, to graph x to the power of 2/5, we're actually going to do it kind of the old numerical way, and we're going to plug in numbers into a table. So let's start from the far left side. So when I plug in -10 in for x, plug it into my calculator, I get 2.512 for y. Plugging in -1, I get 1. And let's get a little bit closer. -0.1, I get 0.398. Let's approach now from the right side. So let's pick numbers that are symmetrical. So let's pick 10. We get 2.512. Substituting 1, I get 1. And then 0.1, I get 0.398. So we can see that as we get closer and closer to 0 from the left and the right, we're actually approaching the value 0. Now, plugging in 0 into x, I can see that my y value would be 0. So this actually gives me a point at the origin. And approaching from the left and the right, I'm actually going to get a graph that looks something like this. So what's happening is, as the limit of f prime of x as x approaches 0 from the right is equal to infinity, but from the left, it's going to be negative infinity because these slopes are going to be going more and more negative. However, in the end, the limit of the absolute value of the derivative is actually infinity. Now, because infinity is not a number, it does not exist, or the derivative does not exist. So we can say that f of x is not differentiable at x equals 0. Now, this graph here that we've drawn actually has a special name, and this function is actually called a cusp. And that means that f prime of x approaches infinity from one side of a and negative infinity from the other side of a. And this is what we call an extreme case of a corner. I'm going to summarize the points of non-differentiability by classifying the most commonly encountered points. So the first type is a point of discontinuity. So from this graph, we can see that it is discontinuous at this point here, so therefore it is not differentiable. The next type is a corner. And a corner is something that is sharp, like this one here, like an absolute value function. The next one is an extreme case of the corner, which is a cusp. And it kind of looks like a bird flying. And then the last one is a vertical tangent. Now this is where we get a graph that looks something like this. And at this point right here, we have something called a vertical tangent. Now at points of vertical tangency, the secant line approach a vertical limiting position. Now at such points, the only reasonable tangent line is a vertical line at that point. However, vertical lines have vertical slope. So the derivative, if it were to exist, would not have a finite real value there. So there's no number, so this explains intuitively why the derivative does not exist at points of vertical tangency.